All right, ladies and gentlemen, how are we doing today? Mr. Dorfler back for another daily dose of Dorfler. All right, in today's discussion, we're going to take a look at more of the methodology of scientific approaches. In the first section that we talked about, we discussed, just the different branches of chemistry and kind of where they belong. Today, going to go into a more of a, like I said, methodical approach into how science is conducted. Okay. So we're going to start off with something that you've probably heard of every year. You've had some science in your educational career, and that is the scientific method. All right. It is defined as a systematic approach used in scientific experiments and research. It is an organized process by scientists to do work and provides a method for scientists to verify the work of others. Sorry, I got an itch in my eye. There are a listing of steps for the scientific method, okay? We have them listed in order, but there's also something I'm going to mention after we go over these steps, just so you understand that they're not 100% rigid. And I mean, like, you can go slightly different directions. We'll talk about that here in a moment. First off, you have observation. Next, you have hypothesis. Then, after you form your hypothesis, you have experiments. You then have conclusions. And then after your conclusions, you have your revised hypothesis. Depending on what you learned after you made your conclusions, revisit your hypothesis. Does it have to be changed? Does it have to be kept the same, or maybe even elaborated more so? All right. Steps do not have to be used in the same order each time. It requires scientists to describe their methods when they publish their results. And so the reason why we have this scientific method is just so other scientists, when they try to support your findings with their own experiment, following your steps, your process is able to be followed and matched by other scientists. And, when they follow your same steps, they get the same results. We can support your findings in your scientific approach. Okay, let's break these down a little further. Let's start with observation, okay? An observation is a scientific study that usually begins with this observation. They can be tabulated, observations meaning it can be dealt with numbers. For instance, if you're just trying to see, right now, how many geese are at the pond in this particular day when it's really cold, you could jot those down and follow that number day in and day out. You can also get different types of data through observation. You can get qualitative data, which is defined as the data that relates to the information that describes color, shape, odor, other physical characteristics, or the quality of those characteristics, okay? Basically anything that involves the five senses: looks, feels, sounds, tastes, smells, all kind of fall under qualitative data. Then you have quantitative data, okay, defined as data with numerical information describing how much, how little, how big, how small, how fast, yada, 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 okay? Quantitative has that word quantity in it, and quantity really means the amount of something. Temperature, pressure, volume, quantity of chemical formed, how much of a chemical is used up in a reaction. Those are all examples of quantitative data. Next step is your hypothesis. It's the tentative explanation for what is being observed. So you have your observation, then you make a tentative explanation that can be testable, okay? That's a huge thing, is the hypothesis must be testable, all right? In this hypothesis, you state what is believed to be happening through your observations, and there's no formal evidence to support your statement. That's where your next steps come in. That's where your experiment comes into play, okay? You have an experiment to see if your hypothesis has any strength to it. Here's some example. Molina and Rowland's chlorofluorocarbons, otherwise known as CFCs, hypothesis, okay? They observed that CFCs were found in the stratosphere. Okay, a lot of times CFCs were found in hair care products, other products that had a propellant, like an aerosol. Molina and Rowland were curious about how long CFCs could exist in the atmosphere. So what they did was they examined the interactions that occur among various chemicals in the troposphere. And from these interactions, they knew that CFCs were stable in the troposphere for long periods of time, and that CFCs will drift up into the stratosphere after they are in the troposphere. Hypothesis was formed then that CFCs will break down in the stratosphere due to, let me move this down here just a little bit, interactions with ultraviolet light from the sun. So the higher they went up, the CFCs tended to break down in the stratosphere while they were in the troposphere, however, the ultraviolet lights could not have as big of an impact. That's why they were found so prevalent in the troposphere and not the stratosphere. So after you form your hypothesis, you then go into experimentation. Your experiments are defined as a set of controlled observations that test the hypothesis. This is either going to confirm or deny a hypothesis by using data. And I actually like to use the words support or not support your hypothesis. Scientists must carefully plan and set up laboratory experiments to change and test one variable at a time. So think about what's going on in the world right now. We've got the vaccines for coronavirus coming out right now. And, we had to come up with specific experiments in order to test the effectiveness of the vaccine on human trials. Then we had to say, okay, now that we've got one dose, how many do we need more than one dose? Which currently they are having a two-dose series of vaccines. And so scientists had to develop these, okay? We had to learn processes, we had to build off previous processes, and we had to develop them ourselves. So we have to determine not only the plan, what is going to be involved, what equipment do we need to have, but you also need to determine variables, okay? And the variables are defined as a quantity or condition that can have more than one value, okay? So you had to think of everything that was going to come into play in an experiment. So breaking that down even further, speaking of variables, you have your independent variable. This is the factor of the experiment that will be changed throughout the experiment, okay? For instance, how much of the vaccine would each person need to be its highest effectiveness, okay? The amount of vaccine given would be the independent variable. You then have the dependent variable. It's the factor of the experiment in which the value changes in response to the change in the independent variable. And there's no control over the way the dependent variable changes. So in this case, the independent variable would be the amount of vaccine. The dependent variable would be the results of the effectiveness. How effective were the vaccine amounts in preventing COVID, okay? So it's essentially the result of your independent variable. You then have your constants. This is a factor that is not allowed to change during the experiment. Besides the independent and dependent variable, all other factors must stay the same throughout the experiment. For instance, going back to the independent variable, if we had to determine how much vaccine was given, but we could also determine the potency of each vaccine. We could determine the strength of the vaccine. If we were using different amounts of the vaccine, we don't want to at the same time change the strength of the vaccine every time we change, because then we wouldn't know which was more effective, the amount or the strength of the vaccine. Okay, so you only change one variable at a time, and so that way you can pinpoint if it's effective or not effective. So everything else has to remain constant. Your control is a standard for comparison in experiments. So your control could be those that were given what's called a placebo, or not given a vaccine at all, and then determine the results of how many of those who did not receive the vaccine were basically being positive for the virus. Those who were given the vaccine, how many of those were positive to the virus, okay? So your control group is basically the group that gets no variables put on there. They stay the exact same way they were at the beginning of the experiment, so we have something to compare it to. So parts of experiment, an example, okay? An experiment in which to test a hypothesis that table salt dissolves faster in hot water than in water at room temperature, okay? So our independent variable would be the temperature of the water, because that's what we're changing. We have the hot water, we have the room temperature water. Your dependent variable is the result, okay? Or the rate at which that salt will dissolve, okay? The results of the salt dissolving in hot and the results of salt dissolving in room temperature water, that's our dependent variable. Our constant would be the amount of salt, the amount of water, and the same amount of stirring. Again, keeping as many things the same so we can pinpoint the exact cause of our result. Again, you don't want to change the amount of salt because the more amount of salt you have, the longer it's going to take to dissolve. The less amount, the less time. Okay, the amount of water is also going to play an important role in how quickly the salt dissolves. As also stirring, agitating that and stirring up that water. Okay, that's going to play a huge role too. And then your control will be the room temperature water. It's the water that has not been messed with temperature-wise. It is simply just water that is at the same room as the temperature. No added heat to it or heat taken away. It's just normal water that's sitting out. Your conclusion now is defined as a judgment based on the information obtained. Form when scientists take the data that has been analyzed and apply them to the hypothesis. So types of results made from conclusions. If the data supports, there's that word support, if the data supports a hypothesis, the idea of the hypothesis may be true. You might have to go even further and gather more evidence to support or not support your hypothesis. You can't just do one experiment. You've got to continue to go. You got to show all pathways that would provide you with this result. If the data does not support the hypothesis, then the hypothesis must be discarded or modified. Okay, if it's just so far off there, you got to start basically from almost scratch. Okay, you got to rethink. Look back at your observations and rethink a statement that you could test that would help explain the observations that you're seeing. A lot of times we have to use models, or we develop models based off of our conclusion. It's a visual, verbal, and or mathematical explanation of our experimental data. It can be tested and used to make predictions. There is quite a bit of theoretical science when you get into certain fields such as chemistry and physics, more so physics. But it's theoretical, but it's explained through mathematical formulas, processes that are very complex, but yet, mathematically speaking, makes sense. Okay, it could, in theory, happen. Speaking of theory, it's defined as an explanation supported by many experiments. It states a broad principle of nature that has been supported over time, subject to new experimental data, and can be modified. So theories are not set in stone. Theories can be adjusted and modified as we gain more and more knowledge. And a lot of times when we gain more and more knowledge, we tend to gain better technology, which the better technology then turns over and helps us gain even more knowledge. Therefore, there are theories out there that are being constantly modified as time goes on because we are able to figure out and find out more information regarding our theory. It's considered successful if it can be used to make predictions that are true. Einstein's theory of relativity. Okay, we don't talk much about it here, but it was studied and experimented, and his theory of relativity has been able to be used and made predictions that ended up turning out to be true. And lastly, you have scientific law, is the relationship in nature that is supported by many experiments. And this occurs when scientists come over and over again to the same conclusion about certain relationships in nature with no exceptions. It just will always, always, always happen. It doesn't necessarily become modified anymore. Scientists develop further hypotheses and experimentation to explain why these relationships exist. For instance, Newton's law of gravity. It was certain that an attractive force existed between all objects, and he proposed his law of universal gravitation, and he found out after a while that, yes, all objects have some sort of attractive force between them. In fact, the computer or device, whatever device you're using to watch this video, you and that device have an attraction between each other. Okay, but there's also something else in the way that is not allowing for you and the device to come together. That is Earth. Okay, Earth being here so close and so large, it kind of supersedes the attractive force between you and your computer or device, and therefore everything stays put. We don't have anything that's going like this. Pardon me, except magnets, but magnets are a whole different story here. But anyway, chapter 1 is all about getting our roots back in science, okay? Learning the basics of science before we continue on, okay? This will help you if those of you who are going into another science next year or even the following year, that we're laying the groundwork for you in preparation for that. But be ready the day after this video is released, you're going to be given your section 1.3 homework, so make sure you are paying attention to that. This chapter goes pretty quick, okay? So make sure you are staying on top of the video and the notes and the homework. Most likely, we're going to have a test on this chapter at the end of next week, okay? So in about a week and a half. So make sure you're staying on top of everything. If you have any questions, please email me, send me a message in Classroom. You always can pause the video and go backward. That's what I like about doing these videos, okay? So, till then, everyone have a good day.